I am Poornima, working as assistant professor in Department of Physics. Today we will learn the topic frame of reference, which includes in the BSc first semester in first chapter itself. The first we will discuss about the topic the frame of reference. It is a very important topic, we should know it. Before we go for the frame of reference, we should know the two basic topics, that is state of rest and state of motion. As you have already know about the motion and the rest, here the word comes the state. The state of rest, state of motion. So here in this state of rest, I'll take an example. Suppose you have a ground. The stone is lying on the ground. With respect to the stone, it is state of rest. Coming to the state of motion, suppose if the car is under motion, if the car is moving. So here the state of the car is under state of motion. Now we have understood the concept state of rest, state of motion. So before we go for the frame of reference, these two topics are very important. We have to understand this concept. State of rest is the particle or an object is not having any motion. Here the body or an object is having under the motion. Now I will consider one more example. If there is a bus is under the motion. The two persons are standing inside the bus and one person standing outside the bus. Bus is under state of motion. Now I'll represent the numbers. This person I'll be giving the number as 1. For this person I'll be giving as number 2. And for this person I'll be giving the number as 3. Now I have to define the state of the person 2 with respect to 1 and with respect to 3. Now see here, in this, with respect to the person 1, this person is state of rest because both are traveling together. Even though the bus is moving, both are traveling together. Whereas for this person who is the observer from the ground, he is standing on the ground. He is observing from the ground. So for this person, to the person 2, he is under the state of motion with respect to the person 3. Now here is a confusion whether the person is at rest or the person is at motion. Both the statement are correct. To know about the statement is correct, we have to have a frame, particular frame. This person is under rest or emotion with respect to whom, that we have to define. To define that, we have to frame a reference. So, for one particular frame, suppose if I am considering this bus as one frame, so when I am defining this, the person state, number 2 person state, the person 1 is observing the person 2 and he is saying he is at rest. It is correct because we are considering this full system as one frame. Similarly, I am taking one more frame here, and in this frame only the two person 2 and person 3 are there. According to the person 3, the person 2 is under motion. That is also correct, and I have framed a frame which is having one person is moving, and one person is standing the ground at rest. He is at rest. He is moving. Now, to define this whole concept and avoid the confusion, we have to know about the frame of reference. The definition for the frame of reference is a set of objects relative to which the motion is described. So, we are describing the motion here. That is called as a frame of reference. So, we have to define the motion which is relative. So, we have defined it here, the frame of reference. Now, under the frame of reference, there are two types of frame of reference. One is inertial frame of reference and another is non-inertial frame of reference. So, there are two types of frame of reference, inertial frame of reference and non-inertial frame of reference. Now, we study the detail of inertial frame of reference. Here, a frame of reference in which Newton's law of motion is valid is called inertial frame of reference. Here, all the frames which are unaccelerated and non-rotating frames are called inertial frames. Non-inertial frame of reference is defined like this. A frame of reference in which Newton's law of motion is not valid. How to describe this? The frame which is having an acceleration and also a rotating frame is called non-inertial frame of reference. And one more thing, in the non-inertial frame of reference, the pseudo force will come in the existence. That we'll discuss later. What is the pseudo force? How it come in existence. So now, based on these two types, we have to derive the inertial frame equation and non-inertial frame equation. How we define the inertial and non-inertial. The first thing we will be considering that all frame of reference moving with uniform velocity with respect to inertial frame is also inertial. First, we will discuss all frame of reference moving with uniform velocity with respect to inertial frame is also inertial. We have to prove this first. To prove this first, we have to consider two frame of reference. So, the two frame of reference I will be taking as S as one frame and S dash as another frame. In a S frame, I'll take O as the origin. So, O is the origin and the coordinate points are X, Y and Z. I have taken one frame of reference, that is S, with the origin O, with the coordinate points X, Y and Z. I have considered one more reference, S dash. For S dash, the same x-axis, origin I will be taking, origin as O dash I will be taking, My coordinate points are x dash, y dash and z dash. Now I have got two frame of references. One is S, another one is S dash. Now S is having the coordinates O, X, Y, Z. O is the origin, X, Y, Z are the coordinates. S dash is having O dash, X, Y, Z. Where O dash is the origin, X, Y, Z are the coordinating points. Now, let S is an inertial frame. That means the frame which we have considered here is obeying the Newton's law of motion. Suppose if S dash is moving with uniform velocity with respect to S along the axis x dash. Now we will be considering the particle P which is moving from the system. So I'll write the particle here. The particle P which is moving from the frame 1 to the frame 2 with the uniform velocity V. So uniform velocity V. At time t is equal to 0, what happens? These two coordinates O dash coincide. These two will coincide because the time is 0. When these two are coincide, my velocity equation will be O dash is equal to V into t at any instant of time. Now, when there is a movement of uniform velocity, I can represent this distance as x dash because there is a displacement has been taken to the point of particle and the whole distance from here to here is x. Suppose I want to write an equation for x dash. So that is coordinates are relating. So when we are relating the coordinates, so we are having x dash, this one, to obtain this equation. What is my full equation? X. This x should be subtracted with this equation, then I'll get this. So x minus O dash will be obtained with x dash. So my equation will be x minus O dash. This is obtained by the motion at uniform velocity the particle has been moved. We have got an equation x dash is equal to x minus O dash. Before we go for further derivation, we have to know some basic concepts for the derivation part. The basic concepts is, we know that x is here, that is a position of a particle. If I change the place of the particle position, then it has become a displacement. That is dx is the displacement. Now how to define the velocity? The velocity is defined as the rate of change of displacement with respect to time. So velocity is defined as dx by dt. Now we have learned the velocity. Then we have to go for acceleration. So acceleration is defined as the rate of change of velocity with respect to time. So dv by dt. But we know the equation for v. Suppose if I substitute that, my a will be equal to d square x by dt square. Now some assumptions has been made here to simplify the equation. The assumptions are, I will be taking dx by dt, I am representing as x dot. The first order derivative I am taking as x dot. And the second order derivative d square x by dt square as x double dot. So these concepts, this one and these concepts are very important. You have to remember these concepts to go further that derivation. Now we'll continue with this. here, as we have written the equation for x-axis, similarly we can write the equation for y-axis. Here there is no movement of the particle along the y-axis. Therefore, y dash is equal to y, z dash is equal to z, even though the z is not having any particle. These three relations are called Galilean transformation relation, for which the particle, the position of the coordinate is referred to the particle motion. Now, here as we have an equation, x dash is equal to x minus o dash. We have an equation for o dash at any instant of time. We got it v into t. So we substitute that o dash in this equation. We get x dash is equal to x minus v into t. This is nothing but the displacement. Now, after getting the displacement, what is the next step? We can go for velocity. How to get the velocity? We have to differentiate above equation with respect to t. So, after differentiating, I will get dx dash divided by dt is equal to dx by dt minus v. So, we got the equation for velocity. So, this equation here, which order is this? The first order. The first order can be represented as x dot as we know it. So, my expression can be written as x dot dash is equal to x dot minus v. Just I have changed the order, the first order as x dot. So, since we have x dx dash by dt, x dot dash is equal to x dot minus v we have got. This is the equation for velocity. Now, after getting the equation for velocity, it is very simple to get the acceleration. To differentiate the velocity, we get an acceleration. So, by differentiating this equation, that is x dot dash is equal to x dot minus v. Differentiate the above equation with respect to t. If I differentiate this equation with respect to t, I'll get, now it is only the first order. After differentiating the first order, I'll get the second order. The representation of the second order is x double dot. So, we can write x double dot dash is equal to x double dot, where v is constant. So, we are not taking that v because v is a constant. So, we have got an equation x double dot dash is equal to x double dot. According to this, what is this actually? This is the acceleration. So, velocity is represented as x dot, acceleration is represented as x double dot. So, acceleration can be written as x double dot. Suppose if I apply this to this equation, I'll get a dash is equal to a. That means the acceleration at the second frame is equal to acceleration of the first frame. Now, here we have considered the particle P, and that particle is having a mass. The mass is multiplied for this. So, mass, when you are multiplying the mass, we will get an equation m a dash is equal to m into a. This equation is nothing but Newton's second law, that is force is equal to mass into acceleration. So, this equation can be written as F dash is equal to F. Here F stands for force. Now, in this case, F and F dash are the forces acting on the particle with respect to the frame S and with respect to the frame S dash. So from this we conclude that the Newton's second law is valid in the frame of reference. So this, whatever the second frame we have considered, that frame is also an inertial frame, and the statement what we have taken that all frame of reference moving with uniform velocity with respect to inertial frame is also inertial, because whatever the force we have at the first frame is equal to the same force of the second frame, and both the frames are valids the Newton's law of motion. So this is about the derivation of inertial frame we have taken as S, and we have proved that S dash is also a inertial frame of reference. By taking the motion of the particle with uniform velocity. When it is uniform velocity, both the frame of references are holds good the Newton's law. Therefore, both the frame of references are inertial frame of reference. Next, we will prove that the non-inertial frame of reference, how it comes existence in the frame of reference. For that, we will be taking that the statement all the frame of reference moving with uniform acceleration with respect to inertial frame is non-inertial. So when the word comes, the acceleration, that frame we are taking as a non-inertial frame. That we will be going to prove it now. Same. Again we will consider the two frame of reference. I'll take this as S as a inertial frame of reference having the coordinate O with the axis X, Y and Z. So this frame is inertial frame of reference. It is an inertial frame. I'll consider one more frame, that is S dash, which is having a uniform acceleration with respect to S. The particle P is here with respect to X. So similar to the previous one, we will write an equation. X dash is this, O dash is the origin here, and this is Z dash, this is Y dash. The distance moved from the first frame till the second frame, the particle will consider here this is X, and the displacement here it is X dash. Now to start with the derivation part, first we will consider the first frame, that is inertial frame. When the particle is moving in an inertial frame and which obeys the Newton's law, it is an inertial frame. So when it obeys the Newton's law, we have an equation F is equal to m into a. The particle which is moving along the axis X. And this equation can be written as F is equal to m into, as we know that A can be written as in terms of X, it is A X double dot. So now the inertial frame is having a force, that is a real force, which is equal to m into X double dot, where X double dot is the second order derivative that we have already studied in the previous derivation. I'll take this as equation 1. Now, at time t is equal to 0, these two coordinates will coincide. When the two coordinates are coincide, make it as one single frame of reference. And it is having, when the particle is start the motion with uniform acceleration, the starting point of that particle will be, this is the starting point. Therefore, the object will be starting from rest. So I'll be taking that is u as 0. Therefore, at any instant of time, the displacement is defined with the equation. I'll just cut down the axis and I'll write the equation here. The displacement can be written as S is equal to ut plus half at square. The second frame acceleration I'll be representing as a dash. Now, we are starting the motion from the initial position where the body is at rest and u will be equal to 0. By applying this, when it is at rest, the S will be equal to O dash. Both the origins are coincide, will be equal to u is 0, 0 into t plus half a dash t square, where a dash is the acceleration for the second frame. So, we have taken all the dashes for the second frame to make a difference between the first frame and the second frame. So, my equation is O dash is equal to half a dash t square. So, we have approached this equation. Now, we will keep this equation and from the diagram, as we have done previously, from the diagram we have an equation x. This equation, we want x dash equation is equal to the same x minus o dash. X minus o dash. This is from the figure we are getting. Now, we substitute for o dash from that equation. So, we got x dash is equal to x minus half a dash t square. Now, this equation is nothing but displacement equation. By using the displacement, we can have velocity, we can have acceleration. After getting an acceleration, it is very easy to get the force equation. Now, we will have the derivation continuation here. Now, in this, as we have got the displacement, if we differentiate this with respect to t, I'll get the velocity. So, I'll be differentiating the above equation with respect to t. As I am differentiating this, directly I'll be using the first order as x dot and the second order as x double dot. So, according to that, x dot dash is equal to x dot minus half a into 2 into t, the derivative of t square. We are differentiating this with respect to t. Here t square is there, so it will become 2 into t. This 2 and 2 get cancels. My equation reduces to x dot dash is equal to x dot minus a into t. Now, this equation is nothing but the velocity equation. After getting the velocity equation, if I differentiate this once again, I'll get acceleration. So, differentiating with respect to t, the above equation. So, I'll get x double dot dash, second order now, is equal to x double dot minus a. Now, we have got an equation x double dot dash is equal to x double dot minus a. Now, just observe the equation 1, f is equal to m into x double dot. So, we can substitute x double dot by using this equation. So, we reduce the equation to that form, that is, I want an equation for x double dot will be equal to x double dot dash plus a. I have shifted the a to that side. So, I am getting this equation. I will take this as equation 2. Now, I am substituting equation 2 in equation 1. So, when I substitute that equation 2 in equation 1, I will get, what is the equation 2 is x double dot dash plus a. So, here I have missed out a dash, just replace the a with a dash. Even if you write the a itself, no problem. But since we have taken for the second frame of reference, represent everything with the dash. So F will be equal to M into, in place of X double dot, we write it as X double dot dash plus A dash. I will be multiplying with this mass into the acceleration plus mass into the acceleration. So this F will be equal to, this is nothing but F dash, and this will be M into A. I'll just rearrange the expression. I want an force on the second frame. So F dash is equal to F minus MA dash. So in the previous expression we have got it, F dash is equal to F in the inertial frame. Now there is an extra component here. M into A is nothing but the force. That force is what we are considering here is the pseudo force or fictitious force. This force is having a direction opposite to acceleration. So I'll be writing this equation, F dash is equal to F plus Fp. Pseudo force is represented as F suffix P. This is the pseudo force, where Fp is the pseudo force and it is given by an equation minus of M into A dash. Now what happens here at the end? What is the conclusion we can draw from this? That is F dash, that is the force of the second frame, is equal to the real force of the first frame plus the pseudo force. So we are concluding that there is an extra force which is coming to the existence for the second frame. That will create that the second frame is a non-inertial frame. So we can make a statement that all frame of reference moving with uniform acceleration with respect to inertial frame is non-inertial. So according to this derivation part, as we can write, as you have taken one frame here and this frame as a inertial frame. When this frame has a particle and that particle is having a uniform acceleration, and that particle uniform acceleration, this frame, we will define this frame as non-inertial frame. So two derivations we have finished. One derivation is all frame of reference moving with uniform velocity with respect to inertial frame is also inertial, where we have got an equation F dash is equal to F. Newton's law has been valid over there. In the second derivative part, all frame of reference with moving with uniform acceleration with respect to inertial frame is non-inertial, and we have proved with the equation F dash is equal to F plus Fp, where Fp is the pseudo force or fictitious force come in existence with the second frame of reference, and that frame of reference we are calling it as non-inertial frame of reference. Till now we have discussed about the inertial and non-inertial frame of references, and the derivation part also we have studied. Now we will conclude this with the two forces what we have studied till now, that is the real force and the pseudo force. The real force is having a physical coordinating point, whereas pseudo force is not having a physical coordinate point. And the real force is, the direction of the real force is same as the direction of acceleration, whereas the direction which is the force is acting, which is opposite to the direction of acceleration. Till now we have discussed about the two types of frame of reference, inertial frame of reference and non-inertial frame of reference with respect to two frames what we have taken